Alright folks, well in this video I want to start talking about the support that different languages provide for abstract data types. So obviously this is a concept that you're all well familiar with, right? Just some way of providing an encapsulation of a type of data and the operations that work on it. And again, should be well familiar to all CS students, right? It gives you the advantages of abstracting away the underlying implementation, right? So that reduces the conceptual load on the developers who are implementing it. They don't care how it's used, and it simplifies the use of it because they don't care how it's implemented, and life is just a little bit easier for everybody. It also simplifies maintenance since you can fix one half of it without needing to worry about the other half. Again, the developer can change the implementation without worrying about how people are using it, or people can change how they use it without worrying about how the implementation is impacted, as long as everybody sticks to that agreed on interface. If you've got a good encapsulation of a lot of data types, that facilitates code reuse. So again, this is a fairly widely acknowledged useful idea. And it is going to lead pretty naturally into our discussions about OO languages and OO features, but we'll save that for a later video. So in terms of talking about some of this stuff, again, lots of languages provide at least some level of support for user-defined abstract data types, right? Creating public interfaces and underlying implementations. The big question is how much of that is just support so you can use that kind of functionality if you want to, and how much of it is enforcement? How much does a language actually force you to split apart the implementation from the interface, and how much of the implementation does it actually forcibly hide from the person using it? And that varies a lot from language to language, right? If you think about something like C++, thinking about structs or classes as our kind of representation of an abstract data type, we've got the support. You can go through and create a class, create a public interface, access the data through the interface, but it doesn't hide the implementation, right? Anybody who can see the definition of the class, anybody who can see that header file knows what the public and private and protected fields are, knows what the data types are, knows what the definitions are, right? They might not see the actual implementations of the functions, but they see an awful lot about the class there. So there isn't that much that's truly hidden. And then if you look at C, right, that's an even more extreme case where it really doesn't support any level of enforcement at all. The developer actually has to make an active effort to get the benefit of abstract data types if they're working in something like C, right? You have to go off and define your functions as global functions independent of the actual data that's enclosed in a struct somewhere. I mean, I guess conceivably you can go through and put function pointers in your struct, but again, you're putting it on the developer to come up with a way to essentially create their own format for an abstract data type, and you're relying on them to adhere to it. There's nothing stopping them from ever accessing the struct independently and the fields independently. So this notion of how much a language provides support for an ADT versus how much it enforces adherence to kind of the principles of abstract data types varies a lot. In terms of the different kinds of features that you might expect with an abstract data type, obviously you need some kind of a syntax so that we can actually create the public interface, create the implementation somewhere, and link the two together so that if somebody refers to something through the public interface, they actually get access to the implementation. So that's kind of a core part of it. But for the operations, what are the operation types? What kinds of operations do you think should actually be supported across pretty much all abstract data types? Obviously, you need the ability to create instances of a data type, to destroy them, although that might be done implicitly. The language might take care of the deallocation for you when things go out of scope, for instance. You're probably going to want the ability to assign one instance of an abstract data type to another, or to copy, right? Copy a list across, for instance, although you're going to have to deal with issues as to whether those should be shallow copies or deep copies. Clearly, you're going to want some way to access the operations associated with an abstract data type, so you can actually ask it to, insert a value or look up a value or do whatever it's going to do. You might want to provide access to the data fields as well, although that's kind of getting a little dicey on the abstract side of things. You probably want the ability to test for equality. Do these two ADT variables refer to the same instance of a data type? Do they refer to the same list, for instance? Or to do comparisons to see if they have the same content? Those would all be reasonable operations. Beyond that, it's probably going to depend an awful lot on the nature of the specific abstract data type you're implementing. You might have some constants or some variables that you want to share across all instances of an abstract data type. I don't know, maybe we've got a circle or sphere abstract data type and we want to share one fixed value of pi across all the instances. Is there some way to do that? Is there a mechanism for having data that's associated with just the individual instances and data that's associated and shared across all of the instances together? Can you do things like create nested abstract data type definitions? So could I have a data type defined inside the definition of a data type? So think of maybe we've got a graph data type. Perhaps inside that, we create an abstract data type for a node that really only has meaning inside the graph, or an abstract data type for a path, again, that really only has meaning within the context of the graph. So is that something that's built in and supported by your language? Can we take abstractions of our abstract data types? So can I create templated abstract data types or generic abstract data types where I specify the operations but don't necessarily give a precise definition of the type? Again, a template or a skeleton to be filled in later once I decide on the data type I'm actually going to use. So these are all things that you might reasonably expect to be part of an abstract data type support for a language or within a language. As far as the implementation issues, there are, again, a lot of things to consider. If we're assigning an abstract data type to another one, assigning one list to another, or copying from one list to another, is it a shallow copy or a deep copy? If I'm passing one of these things as a parameter, am I passing an actual replica of the entire thing, or am I passing a reference to it? What kind of implications does that have for the stack space if I'm passing a copy? What kind of implications does it have for side effects if I'm passing a reference? Right? Those are all things that you want to know about how your language is handling abstract data types. Earlier when we were looking at structures and arrays and that kind of thing, we considered the possibility that they could, if you've got a local instance of something, they could be allocated in the stack space for that particular function call, or they could be allocated off in a heap someplace with a reference from the stack space. Same sort of issues are going to apply, obviously, with our abstract data types. If we've got functions or methods, right, the actual operations associated with our abstract data type, suppose we've got 12 different instances of a stack, and we've defined a push operation for stacks. Do they each get their own copy of that push code? Or do we have one instance of the push code someplace, and it gets referred to by all of them, and somehow when they call that stack, that push, they're letting it know which stack is calling it, and therefore which one needs to be pushed to? So again, these are implementation issues that we have to take a look at. So what we're going to do is we're going to move on and talk about the object-oriented side of life, because many of these same issues are going to be a focus in OO. So we'll look at the implementation details after we've done a bit of discussion of the OO theory. Oh, that's where we'll go next.